Hi, everyone. This is Will. Welcome to what I think is the sixth intro series hangout on miniKanren. Got a special guest today, Dan Friedman, co-author of The Reason Schemer and co-creator of miniKanren and co-creator of Kanren before that, and someone who's been in logic programming a long time and functional programming and all these sorts of things. So Dan is here because I was working with Dan on writing a book, and I kind of ran out of time before the hangout, and I wanted to show something, and I wasn't 100% sure that I was going to remember all the details off the top of my head. Dan's like, "Well, I can give you some backup." So Dan's gonna give us some backup, or maybe lead us in adding letrec to our interpreter using what are called half closures, and maybe Dan can explain the history of that through John Reynolds and all that stuff. Before we get into that, I just wanted to mention that next week we're not going to have a hangout because I'm going to be in North Carolina hanging out with some functional programmers. But after that, I'll be back. So no hangout next week unless people want to get together on their own. That's fine. Okay, so Dan, do you want to explain where this idea of implementing letrec or what this half closure thing is, or where it came from and who developed it or whatever? A little of the history.
I don't know any of the history of this. In fact, I seem to recall that I had this weird idea, but I'm not sure. But you know, a lot of things work that way. You then find out someone else did it, but it never emerged. And I may have been that Mitch explained it or came up with the idea. I can't remember because when we're writing books, going and you don't remember exactly where things come from. So it's in one of the essentials. It's probably in two of the essentials, I'd say.
Well, you have to explain what the essentials are.
Oh, essentials is a book by Mitch Wand and Chris Haynes and I. And it's in the first two editions, it was with Chris, and then the third, Mitch and I went off on our own to put that third one in. And it's a book that's got a little bit of
What's the title of it? You still haven't said what the title is.
Programming languages. That's what was happening to me yesterday, by the way, all the time. So it's called Essentials of Programming Languages. And it's a book on programming languages that basically tries to teach you how to understand interpreters on a deep way, and then show you how to do some other things like write a type inferencer and a few things. And I'm not trying to sell it because it's not my name. But I will tell you that if you don't understand all of this, you should be able to find it in probably in number 2 or number 3, second or third edition, but I can't even be sure of that without going to my little shelf over here and looking it up.
Okay. Well, now you sent me an email, I believe, a long time ago where you were describing this, and you said that this half closure approach was described by John Reynolds in his definitional interpreters paper.
Or maybe it was then. And
So
that would be the place where it might have emerged first, because he was really that would be it. I mean, I didn't really have a good time with John's paper.
It was a hard paper to read.
Well, it wasn't so hard as much as it was not my style. I like things a little cleaner than they were appearing to me at the time. In any event, it's a wonderful paper, heavily referenced paper for all the good ideas, including continuations and stuff like that. So, what you call escape procedures. You're going to write a line of code in your interpreter.
Okay. Yep.
You want to see, and it's going to start out with however you're writing your pattern. Are you using match or something like that?
Yeah, I'm using pmatch.
Okay.
This should all be very familiar to you. So
Okay.
I've got a version of the interpreter, which you should see on the screen now.
test on the screen. Yeah.
Well, we got our friend eval expert.
That's what we want. Okay.
Right?
So
Okay.
you just throw in a PMACH clause that uses parentheses letrec.
Okay, so we've done a few versions of the interpreter, so I should just say that this is the first order representation of things, and it's not a representation. It's not the representation independent.
I'll find my way when you are typing it in. Don't worry.
No, I'm talking about this for the audience, not for you.
Oh.
I know you know what it is. All right, and then I'm going to add. Let me add a vowel. Well, the driver, I guess. What did I call it before? I don't remember how I did this before. I did like.
By the way, one of my claims to fame is I was your teacher.
That's right. I've mentioned you several times. This has come up a few times. And then here is our empty end, right? So
yeah, that's
nice
touch.
We actually use empty end for, yeah, I do have something called empty end. Great. All right, so we've got a little thing called a val, although that's a little dangerous to call it a val because we're shattering schemes of val, but that's fine. I'm going to live on the edge. All right, so now.
Just so you know, for the record, we were calling we kept normal form operator eval. This is in a different book. And we switched it to val of because it just could confuse someone who understands eval because they're completely there's no overlap.
You mean schemes of val?
Yeah. So that's why we switched that word up on the top.
So you call it value of.
VALOF with a hyphen, but you can leave out the hyphen if you want.
Val of that?
Yeah.
Ugh, yeah. No.
Well, too bad.
That's value. Oh no, we're calling it val. Forget it. All right. Anyway, that's how we're going to do it. Now, if you want to change it at home, that's fine. You can change where you want. Okay. So now we're going to add a new line. We're going to add letrec line, right? All right. So let's. Do we just want to do a simple one that's going to have like one definition, and we're going to assume the right hand side is a lambda.
We put in two.
You want two? Oh, so we can make something mutually recursive.
Like even and odd, for example.
Sure.
You have shown even and odd?
I don't know if we've shown even or odd.
I think I would show even and odd as an example to show why you'd want.
Have I shown even and odd? If not, well, we'll do that. Actually, okay. So before we add this, let's just go to scheme and remind ourselves both of what letrec looks like syntactically and how it works. So with letrec, I can give a name to a value, and usually, almost always, it's going to be a lambda on the right-hand side.
It should always be. Extensions that have been thrown in are very, very weird, and especially in a call by value language. I would not use them otherwise.
I can define factorial.
Mm-hmm. Times n, factorial sub 1 of n.
Thank you, Professor. All right.
We're entitled to be tired. We weren't.
All right, so we're gonna do factorial 5. All right, 120.
Fair enough. It's still 120.
That's right. Okay, so
no, you can do some wild things now if you want to.
Which is what?
You could change put a let outside of the letrec. Actually, you do it with let. Never mind. Sorry.
Okay, so this is just a recursive definition, and this would be equivalent if we were at the top level to saying something like define, and I can just literally just grab that lambda, right? And that's going to be the same thing, except this will be a top level definition. So these are equivalent, except now if I do this definition, now I have a top level definition of bang. Whereas with the letrec, the scoping of this bang is only within the body of the letrec. So if I stop scheme and restart it, there is no bang defined at the top level. That's just, that doesn't work. If I do letrec, that's fine. I can call bang within the body of the letrec, but bang still isn't defined at the top level. Whereas if I use define, now it's defined at the top level. Okay, so we can use letrec as a way of, defining recursive functions where the name of the function is bound only within the body of the letrec, and we're not sort of polluting the top level namespace. Also, top level define has somewhat different semantics than sort of the rest of scheme where you're using lets and letrecs and lambdas, and it's a little messier to deal with. So letrec in some sense is kind of cleaner if you want to think about semantics and implementation and so forth. So letrec's what we want to do. And what Dan was, go ahead. So should I do even and odd?
Yeah, might as well go. The whole 9 yards.
Whole 9 yards. Okay. So
feel that one.
Let's do. So first of all, scheme has even, so I can ask if 5 is even. It's like no, false. Is 4 even? Yes. And similarly, scheme has odd. 4 odd. No is 3 odd. Yes. Great. Let's define even and odd using letrec. And we are going to define this in sort of an interesting, unusual way. If you may have seen other ways to define even and odd, but we're going to do it a little bit differently. So we're going to say for even, if even's going to be a function, takes a number. If that number is 0, well, is 0 even? Yes, 0 is an even number. Otherwise, what are we going to do? Well, I've taught you the game that Dan taught me that we play, where we make a recursive call. And since we're asking a question about n, we have to get n close to the base case. And since n is a number, we get closer to the base case by subtracting 1. It could sound like that. That's one way I can do it. And then I could add some sort of test on the outside. But
that won't work. You know that won't work, right?
Well, I could do.
It won't work. You could do sub 2.
Well, is there no way I can put a test on the outside?
No, you don't want to do that. Here's what you want.
Well, I know I don't want to do that.
Okay.
Right. So in fact, we're going to do like a different pattern recursion. We're going to call odd instead. And so what is your intellectual justification, Dan, for making that odd?
Be sub 1?
Yeah, odd of sub 1.
Yeah, you want things to be as simple as possible and not be concerned about execution time until the appropriate place, whenever that happens to be. And that is why I teach this one, because I want everyone to understand what mutual recursion is. I mean, usually you just want to look at a bit to find out if it's even or odd in a number. So hardly, no matter what you do with this other code, you're not going anywhere. On the other hand, these are staying as piano numbers. And so
piano numerals. These aren't piano.
Basically, n would be a piano number because you'd have a bunch of add ones outside of it. And then when you do the sub ones, you basically just cutter down the equivalent of a cutter down the sub 1 as the sub 1. And so that would work as well. Okay, so that's one of the reasons you do this. You just do it because it's pretty and elegant and simple, and the properties we look for. Okay, moving on.
So basically, we're trying to illustrate the idea of mutual recursion. All right, so the point here is that even question mark or even is defined in terms of odd question mark or odd and within the body of the letrec, we can refer to even or odd. And so we can call even question mark of 5. Now this isn't schemes even, we're shadowing schemes even. But if we run that, it works. And if we run that before, it works. And the point here is that even question mark for n greater than 0 is going to end up calling odd of n minus 1, and odd will end up calling even, and just toggle back and forth until finally you reach a 0 case for either even or odd, and then you'll get back true or false. And of course, what happens if I do even of -1? Well, that's going to go in an infinite loop. Okay. So we're going to have to make sure that we have non-negative integers as our inputs. And if this were, a really big number, we'd be doing lots and lots of recursions. But fortunately, Shea schema is pretty fast. So, but at this point now, you can start seeing it takes a while, right? So, whereas if you, like Dan pointed out, if we were just looking at the last bit, it would be fast. Okay, so that one sort of took noticeable time. So if I time it, all right, that took 263 milliseconds or something.
It's unbelievable.
Yeah. So if we were doing this, sort of.
This is millisecond? Oh, it's because of the period there.
Yeah.
Oh, maybe it was 28 milliseconds. No, it couldn't have been. Okay, never mind.
Never mind. Okay, but the point is we can define mutually recursive functions this way. Before we were doing factorial using the Y Combinator, or a variant of the Y Combinator. Actually, what Dan calls the poor man's Y Combinator, which I guess is technically the poor man's Z Combinator, because we're going to call by value. And so sort of this kind of awkward encoding of factorial, if you remember that. Whereas when we have letrec, our definitions can be much nicer. And also here we can support mutual recursion. Okay, so we're going to add a version of letrec to our interpreter so we can write recursive definitions. And what Dan was suggesting is that we have a version of letrec that lets us define two bindings here for functions. We are going to restrict letrec to have lambdas on the right-hand side of the variable bindings. So this is actually not required by scheme. You can have any expression you want. However, you're not allowed to refer to this variable on the left-hand side until you reach the body, which in practice usually means you want to have a lambda on the right-hand side. So by restricting the right-hand side to have a lambda, in practice, we're not really losing much power of interest. All right, so let's try to come up with a pattern, a p-match pattern that's going to match this sort of structure. That's what we're trying to do now. So let me go back to the interpreter.
Let me correct you.
Okay, go ahead.
I couldn't figure out the right words for it, but now I do.
Right.
You can have even appear on the right-hand side as long as it's hiding under a lambda somewhere.
Yeah.
But you can't evaluate it.
Well, you can't reference it.
You can't. Yeah, you can't reference it unless there's a lambda above it somewhere. Okay, so it doesn't have to be where it says lambda n at the very top. It could be, the lambda could be down further in the data structure. So you can create graph structures with this thing as long as some of that is lazy. All right, so you are allowed to have it on the right-hand side, and you also are allowed to have it in the body, but there are restrictions on using the name in the right-hand side. That's so. Well, for example,
the rule is you cannot reference it. You cannot reference one of these binding names, right? And you cannot reference it until the body is being evaluated.
That's it.
You can't reference it in the binding expressions when those get evaluated.
In there. So, for example,
they can appear in there, but they cannot be. You cannot perform a variable reference when you're evaluating this expression. If you look up even question mark when you evaluate this right-hand side, then it's an error.
Mm-hmm.
Right. That's all. We're saying the same thing, but yeah.
Yeah.
Okay, so that's important. So by restricting us to have lambdas on the right-hand side, which is more restrictive than scheme, we sort of automatically meet this condition.
That's good.
Yeah.
Okay, so let's write the line now.
All right. So let's write the line.
Let's take a look at how you represent closures in here.
Okay, well, you can see it right there.
Okay, that's
The
all.
landline. That's the closure line. And we're using an association list representation for our
Perfect.
environments. Okay,
You're all set. So
we're all set.
if you're going to put into, would you want to call the second one maybe G?
Yep.
And the argument maybe Y?
Sure. And maybe we call this.
Everything else is curried. Is that my assumption? Correct?
Everything else is curried. That's right.
Yeah, there's your radar ran line. Okay, that's what I mean.
Call this the F body and
Yeah, FB. F body's fine, whatever.
yeah, F body and
Body. Okay, so here we go.
oh, well, we're not done.
Well, yeah, you got to put a body in there.
Put letrec body.
Sure.
Does that look like a good pattern to you?
It looks like a perfect pattern. Now, I have a question for everybody who's watching. Are you lost yet? Anybody?
No, I'm good.
Okay, that's just want to make sure everybody's fine. Did we lose anyone? No. Okay.
Well, we may have lost some people because I know at least one person's a little behind on the last one, but that's why we're recording it. So
I'm suggesting that they might want to blurt out a question if they get lost. Okay, that's all I'm asking.
Okay.
All right. So now what we want to do is we want to extend the environment with a tag. We'll call it letrec for want of a better name, and we will place in that environment F bound to a half closure, a dotted pair now, or a list of pairs.
What is your letrec in things? Are we going away from association lists, or are we still having association lists?
We're going to have something like an association list, but not yet. Okay.
Well, are we having an F here in the left-hand position then, or not?
No, not yet. We're going to after the word left.
All right. Well, tell me. Am I writing it right so far?
And now we want to write an association list here. So pren F. And now you take everything that you see up there and turn it into a half closure.
The entire thing, the whole set of bindings, or the entire letrec, or what?
To the right of the F with a comma.
Just the lambda.
Well, no, you want to actually pick up the whole closure for it. You see the closure tag, the way the closure tag sits there?
Yeah, up here, you mean?
Mm-hmm.
Yeah.
Just pick up that whole thing, but do it for this other these two lambdas.
You mean for FNG?
Yeah. Just like that for the first one. Close the F. Put your commas in, yeah. And now do the same thing for G. F body and right. Well, you're not going to have an M because it's a half closure. There you go. Now do the same thing for G. Okay, so now you have almost what we want, but we have to extend, we have to be able to use this as the thing that extends the original environment.
Okay.
So I dot env maybe or something. No, just env, just plain old env. That should do it. Okay. No, I don't. Do you want to do that? You're using. Are you doing a? So it's just one A list, right? So yes, you probably want that dotted.
Well, so we're not an A list anymore though, because we got this letrec env tag.
I know. So let me think for a moment.
Are we going to a tagged environment representation? We've seen those before.
That letrec is a tag.
Yeah.
Yeah. I don't want to mess that part up too much. Yeah, I think you might probably want to leave the dot there. We'll see if it works. Okay, so that is the definition of letrec env. And now we have to change lookup.
Well, we have to evaluate letrec body in that environment. Well, I mean, we haven't done a recursion yet. We have to do an eval export, right?
Right. I call eval, whatever. Of letrec body, yeah.
In an extended environment.
In this new environment. Okay.
All right.
All right. Now, having done that, we have to change our definition of lookup because we've added a new kind of entity that goes into the environment. That's why I'm a little nervous about the dot. I haven't thought about it.
It seems like we should tag both if we're going to tag letrec.
Dot to make sure that it's an easier thing to think about. Yeah. Okay. Now let's look at lookup.
Well, here's the other environment we're creating. Can you turn down your volume or put your headphones on?
I can put my headphones on.
That'd be great.
All right, where was I?
Well, I was pointing out that we have another representation of the environment right here. In apply proc, we extend the environment. So this is not a tagged representation, but we have a tag representation here. So it seems like we have a mismatch between the two environment representations. Should we go back?
You could add an extra tag with my blessing.
Because we've done a tag, we've shown tagged representations of extended environments. So this, where we had like xenv type thing.
Yeah, that's fine.
Right? Where we had x. So something like that.
Perfect.
Or we could just call
that's a nice way to look at it.
Okay.
It makes it a lot clearer. But now I want you to run your test programs before you go further, though.
All right. Well, let me look at my empty env first.
Empty env should still be the empty.
So empty env is going to be now empty env. Like that. So we played this game a little bit.
Okay.
So now lookup is going to be a p match on env. And now instead of doing a null test, I'm going to check to see if I got empty env. And otherwise, you look at my xenv. Otherwise, we're going to have an environment that looks something like this. This is where we can decide where to put our hats. I guess I'll put my hats this way. So in this case, I better call this Y. I guess I'll just do it this way. This is where it gets tricky. Where do we put
because
hats
you're
on
going
things?
Because you're going to miniKanren?
No, this is just because I'm going to have to. I don't want to shadow these things, right? There's I could call it old val new. I've got an X and an N, right?
Yeah.
So, I guess the other way is.
No, you're right about worrying about the shadowing.
You have to, you just have to be careful with the names. That's all. That's all I'm saying. So we can say if X and Y are the same, that means we found it. Now, otherwise, we are going to do a recursive call lookup on Y and env. I think that's right. Does that look right?
Oh, M, that's the difference. Okay. All right, so you now have a nice little lookup function. All right. Okay. You want to test this program, please?
I do.
Just run the same set.
We've got a bunch of tests already. So first order.
I saw that.
Load first order interp. SCM. So I may have been. Oh, I think I have some tests where I have custom environments. Yeah, so I'm testing the environment lookup. That's fine. We can fix these as well. So yeah, I think I have 2 with the non-empty environment. Okay, that's fine. We can just go back and look at what our xdiv looks like, get that format. So we can still test these things. Of course, we could build these up to be representation independent. And
Yeah, but this will do for now.
yeah. So this is empty env. And
You need to make that a back quote.
Yep.
Not a quote.
I'll do that.
There you go.
Okay.
All right. What else you got?
And the same, we got one more test like that.
All right. Let's make sure these are working before we go much further.
Yep, they all work.
Now that Y doesn't require a comma. Maybe not.
No, because I'm literally looking up why.
You're quoting it. Okay. All right.
That's the. Okay.
Give it a shot.
All right. So that I just tested it. It runs.
Oh, it ran then.
Yeah.
Is that correct?
Yeah.
Yeah. All right. Excellent.
Okay.
All right. Now we can get
So
back to the
this is
interpreter.
a little faster than we usually move, but
Oh, okay. Well, you can
but
always-
we've gone through all these concepts. So you know, that's why we're recording it. Someone can rewind. But basically, what we just did is we changed the representation of our environments to go from an association list to a tag list. We'd gone through all those steps before, and I just changed those examples, the two examples that test the environment lookup directly, to use the tag list. And now we have two different types of tag lists representing environments. So we have the regular extended environment or empty environment, and then we also have a new type of extended environment, which is a recursive environment. And so that's what we're going to get when we have the letrec clause.
So now what
we're
you
creating
want
a
to
special
do,
type of environment.
now you want to look in your lookup again. Go back to your lookup definition,
Okay.
and search for a letrec environment.
So here's our letrec. So we're going to add. So we have cases
The order
for
doesn't
the
matter.
empty environment. That's true because it's fully tagged. It doesn't matter. We have the empty environment, an extended environment, and a recursive environment. I'll put the recursive environment last, I guess, just for fun. And or do you
I'm
want me to put
afraid
it
that
first?
I'm worried that the empty and you're making a mistake with the empty environment. Up here, it's with parentheses. Is it that way elsewhere?
Yeah, I just ran all the tests. Here it is. Here's empty
No,
env.
but you didn't have any unbound variables. This empty env has to have parentheses around it under eval. Or take them off there, whichever you want. You can't do it so easily with PMatch.
Wait. What?
The third
what's
argument, you see the definition of eval? Define eval.
Yeah, but this is a variable reference. This is a variable reference. Empty env happens to be bound to a list containing empty env.
Oh, okay, fine.
This totally works. Now
Yeah.
you could say that maybe I'm playing a little bit too much of
No,
a game
why
with the
don't
names,
you?
but this is exactly what I do in C311.
Yeah. Yes, that's what we do, and I thought I didn't see that one.
Yeah. Yep.
Got it. All right, now let's look
So
at
just to make that clear, if I type in empty env, you can see that I've got a list containing the symbol empty env. So that's what we're talking about. So,
yeah.
but this is why in these examples with a concrete environment, actually this is a concrete environment too. I should change those. But that's why I put comma empty env, because I want to look up the variable. So technically these are also not right. So Z to be 17. Let me fix those. Z 17. So Z 17. Environment going. And of course, we've seen how you can make this code representation independent, where we could have functions to extend the environment and functions for the empty environment and all that. So that should all work. Let me just test it again.
Oh, empty env is unbound. I told you
it's because
I was
it's
uncomfortable.
no. It's because of letrec. We haven't finished letrec. That's why it didn't work. Because we haven't said the right-hand side of letrec.
No, we have not. Oh, you put in the pattern match already in lookup. It should just be parentheses letrec, letrec m.
Oh, hold on. We actually are getting an error though. Now that I fixed the Z7. Oh, okay, now I know. So the problem is the answer I expect to get back is wrong. Yeah, I'm just updating my tests here.
Yeah.
So that we should get back that, and it should have the list empty in actually. And I think that's the only closure. Do we have any other closures? I think that's the only closure test we have.
Okay.
Okay, that's all fine. All right.
All right.
So everything works now. So let me grab our environment. Let me go back to the lookup. And let me add a clause here. There we go. So we're all good. Now we just have to add the recursive environment case.
Right. So now here's the trick. When you see that letrec m, you're going to eventually be generating a real closure. You shouldn't call this closure, by the way. Half closure or something like that.
Okay.
And these have to be in the very same, we used to call them ribs. Okay. They have to be in exactly the same ribs because they are mutually recursive. Because you don't have any choice.
Describe what a rib is.
Well, a rib was given to us by Guy Steele, who is represent the association list as take all the stuff that's in the first part, and that was only for the lambda terms themselves. So if you had lambda ABC, the parentheses ABC would be the list of variables, and the values would be whatever the values were. That, and then you have a bunch of them, and you hang them like you hang meat from a locker. In a locker, then that would be equivalent to what looks like the ribs. On the left-hand side of the ribs, each rib would be the list ABC or whatever the formal parameter list was. And on the right-hand side, the list of numbers or whatever they happen to be bound to. And so each one of those would be a rib, and you look them up in that using that technology, knowing that representation. Now,
forget I asked. Okay, let's keep going.
It's actually a very cute trick, and it speeds things up conceptually when you're teaching it. When you have then curried functions, which you get all the time in Scheme. So if you actually want to implement Scheme, the ribs are pretty good. All right, now.
So I still don't know the rib is. Okay, let's keep going. So what do we do now?
Okay, so our next thing to do is to write a recursive function here that will look up all of these things and include in them, we're going to take another copy of this letrec m, store it at the end of a real closure when we're all done. But we have to find this. So we're looking through it, and we're looking, and now we finally come to the letrec m, letrec m's in your code, not just this one. So we have to be careful to actually get this particular one again, sort of. Okay, so here we go. We're going to do we found it, and so now we're going to do an ASCII. But you're actually going to set up a recursion. So let's let's do the ASCII first, and then we'll back into the letrec. ASCII of letrec m of f, let's say. Okay, so hold on to that pair.
Wait. On the what?
With quote letrec.
ASCII QF of what?
Oh,
we have to give it a list.
Yes. Well, you're going to give it the second thing in the letrec env.
What is that?
Of pairs.
What do you mean the second? What? What are we looking up F in?
In the first thing after the tag.
You mean this thing?
Yeah.
Well, we know what the ASCII is. It's this, isn't it? Isn't that exactly what the head? Or well, that
but
whole
you got to
pair
be
is
sure
the
that
ASCII.
F is. You have to be sure that F is there. There could be other ones.
How?
You've
Well,
got to find the one that has the F. We did even and odd, right? So F could be even and G could be odd. You agree with that?
I agree with that. But why are we looking up F instead of G then?
You're going to look up F, and if it doesn't find anything, you're going to look up G.
Doesn't F have to find this?
No.
How could it not? F is now
I'm sorry.
bound to
That's
this.
Y. F is Y. I'm sorry. I see
Oh.
where I'm confusing you. Looking up Y in that thing. Very nicely done, William. Okay.
Okay, so
now
let's remind people, because I'm not even sure if we've said this, what ASCII does. So assoc looks up a symbol, foo, quote foo, in an association list. So if bar is 5 and foo is 6, as 3, then we get back the pair.
the whole thing.
The whole thing. And ASCII is the same as assoc, except it's designed to work on symbols. So in this case, they're going to behave the same because we have a symbol we're looking up. But there may be cases where we have numbers that are really large or things like that, where assoc has the semantics of EQUAL instead of EQ. But anyway, so we're doing this ASCII thing to look up a symbol in association lists, and it's going to give us back the entire pair. So that's what's going on with this use of ASCII. So we're looking up whatever Y is the variable we're looking up in the environment. We're doing an ASCII on Y in this list. That's binding F to this one half closure and G to this other half closure. So we're going to get back presumably a half closure if it's in the list. Otherwise, that's going to be some sort of. Otherwise, we're just not finding it.
You're going to get back the pair, comma F dot, and then a half closure.
We're going to either get back F dot half closure, G dot half closure, or we'll get back hash F, which means that we didn't find it. So if we look up a symbol like dog, which isn't in the association list, we'll get back hash F saying couldn't find it. Right. So we could get 3 values back.
You better
back,
hold on to that value then, don't you think?
Yes, I think so. We should give it a name, give it a let binding. So basically, we're either going to get back F dot half closure, G dot half closure,
or false,
or we're going to get back false. That's right. So let's give that a name. So we're going to let bind.
Call it
something.
H.
Have to give it a name.
H closures or something. Maybe
H closures. What are H closures?
Half
Half closures?
Yeah, half closures.
Well, there's only one of them.
No, there's 2 of them.
We're only gonna get the ASCII is only going to give us back one of them.
Oh, you're going to get one, or you're going to get okay. You call it hash closure, half closure.
Okay, so we're going to get back one half
nice.
closure, hopefully, or we're going to get back hash F. All right.
So now you got to make a test to find out which it is.
Okay. If half closure is true, that means we found a half closure. Otherwise, we didn't.
That's right.
If we didn't, do we look up?
You'll do another lookup.
Environment.
Yes, we'll do another lookup.
Okay, so it's recursive in that case. Okay, so if we didn't find a half closure, we look up Y in the old environment, right here. This environment, is that right?
Yep.
Okay. All right, fine. However, if we did find the half closure,
a real closure. Otherwise, we want to return a real closure. So now we have to know whether we had if we found it to be, well, we know the name, right? It's Y.
Yeah, that's true.
So
Does it actually matter which one it is?
You only change one of them because you're just returning a closure now. So if it's F, a closure made with X and F body, and if it's G, you want to have closure.
I guess I'm saying we could p-match on. Actually, that's the way to do it. The p-match on half closure.
You could.
So there are only two cases basically. If we pattern match on the half closure, if the half closure is false, then we recur.
Oh, you're p-matching on the
okay. Yeah. Otherwise, we actually found a half closure, and we know what that pattern looks like. It looks like, maybe calling it F is unfriendly. It's like H, Z, H body.
You could do that.
Right. So that way, it doesn't matter if we match on F or G, because I assume we're going to handle them the same, right?
Yes, you are.
Yeah.
But you're only going to do one. You're only going to do one. You're going to make a closure.
I know, but it doesn't matter which one it is.
No.
Okay, so now we're going to create an honest-to-goodness closure. Right?
Yeah.
Like a real closure.
Right.
So it's going to have an H body.
H body.
And now, okay, Z, H body. And now the tricky part, or the interesting part, is the environment we're going to give it, right?
That's correct.
Okay. And so which environment do we give it?
The one you entered with.
So that's inv hat.
Correct.
It's the inv hat coming in here from lookup.
Yes.
And that's the tricky part. This is the interesting part because the inv hat actually contains the bindings for F and G to those half closures.
Correct.
Yeah. Okay, so this is pretty subtle.
You bet.
All right.
It's very.
So how would you try to explain this half closure approach then? You know,
well, I wanted a solution that when I wrote the book, I didn't know it was in Reynolds 73.
Okay.
But I don't recall, as I said, whether Mitch proposed it or not. But I wanted one that didn't have any side effects, because if you have any side effects, even doing things as simple as miniKanrenizing is impossible. You just can't do it. But now it's a real closure. So whenever it looks things up, it looks it up in the environment that existed at that very moment in time. And so if you go back in there, G or F, whichever one you didn't get in the first place, you'll get the right one. And of course, we want to demonstrate that with the even and odd.
Okay.
Right? Now let me just look at it. So it doesn't matter. That's it. That's it. Okay. So.
All right. So first of all, let's just load it again and make sure we didn't break anything.
That's always a good
and
idea.
our test pass. All right. So now we're going to add another test.
You got to give an even and odd test now.
Yep.
And then we'll give it the ultimate test.
All right. So here's our even and odd. I think we have if 0. Let's see. Let's make sure our interpreter has all.
Oh, you don't have those operators in there yet?
No, I'm not sure. We may not have the booleans. Let's see. Do we have? Whoops.
Add them.
Well, I know. I just want to make sure they weren't there before I added it. All right. So let's add booleans.
Just historical remark, I fought for Boolean question mark. Revised, whatever. It was a battle. Oh, and you can just I wanted a predicate. I didn't want to check for hash T and hash F if I just wanted I just needed a predicate. Because, this game has a strange behavior with things that it's not with things being truthy, so to speak, and I don't like it.
Yes.
So
anything other than true, anything other than false is true. That's what you're talking about.
Yeah, and I hate that.
Well, yeah. All right, so is 6 even? I think it is.
So let's hope.
So I'll call that one even 6, and I'll call the next one even 5. So that should be false. All right, let's see if these work.
What does that mean?
Exception in P match. Match failed.
Oh, that's no, that should work. Hold
on. Now, which P match is it failing in is the question.
Yeah, we use P match who? Do you have P match?
P match who? I don't know what that is. I suspect not.
It tells you which. Oh, actually, it's going to be the same. There's only one use of P match, so it has to be the only.
No, there's not one match. There's not one use of P match. There's
but for this system, there's only one.
Well, there are 3 uses of P match. It could be actually.
Oh, that one.
Well, it could be.
Like it's red. Oh wait. Oh, you're not using that part of it. Okay, never mind.
Yeah, so I'm not sure. It's either the half closure P match, the P match on the end pack coming in, or it's the P match on the val expr. So we can trace these things.
Okay.
Trace. Val expr. Am I getting the syntax right? No. Yeah. And then trace lookup. Wait, why did that? Should have seen a bunch of stuff coming out.
You do have sub 1 in there, right? Surely you do. Yeah, I see that.
All right. Trace define. And let me trace define. Look up. Okay. There we go. Okay, so we're calling a val expert with that. P match failed. Okay, so it looks like the val expert is where it's failing.
That would be bad.
Was there something wrong in my?
Are you allowed to use small? Are you allowed to use small lambdas? I guess you are. Oh, put a comma in front of that lambda.
Oh, I didn't put a comma in front of letrec body. No, the lambda shouldn't have it. Letrec body needed to have it. That was the problem.
Yeah. Okay.
Yeah, so we were literally matching the symbol letrec body.
So far it might be correct.
It might be correct.
Might be.
Might be correct. It is not correct, it looks like.
Correct. Okay.
But we got further. Well, actually, wait. So we got that one seemed to pass. No, sorry. Okay, so we got the even, odd stuff. Lookup in, empty env, unbound variable in. Okay, so let's look at that.
Oh! Wait, whoa! That's these. That has to be a closure. Go back to the code. I have an idea that what we may have forgotten to do. I think we have to.
You mean the lookup code?
No,
It has to be in the lookup code, right?
Closures. Okay, yeah, it has to be in the lookup code. Hold on.
So basically, it was saying that the n was unbound, and n is the the variable
The
for
formal parameter of the lambda.
Okay.
So I'm trying to figure out why that didn't work. And that's sitting inside the half closure.
Yes. Yes. So both x and y are in our particular case.
Right.
So if we hit the false case, that could be happening. If the ASCII isn't working correctly. Let me print out half closure here. Oh, it's false. Yep, that would be why. So something went wrong here. Do you see that, Dan? Still with us, Dan? You see that? So when we're doing AskQY in that list, so we must be looking up in, right? We're looking up in. Okay, and that's fine. So when we're looking up in, but when do X and Y get bound? They must be bound when there's a procedure application, right? So did I call it? Let me look at apply proc. That's when that gets bound. Closure X body env. Okay. Closure X body env. That's fine. And then evaluate the body in an extended environment. So let me trace apply proc. So let me try this. I'm not even seeing a call to apply proc. Oh, yeah, there's no call to apply proc there. Can you hear me, Dan? I can't hear you. I can't hear you. I think you lost your audio. You might have to rejoin, Dan. Not sure. Okay, well, there's definitely something not right with our lookup because we're trying to look up in and we're getting the wrong thing. So let me try try a test where I'm calling these different. I'll call it M. Call it M in the case of odd. Okay. So the half closure looking up M, it's finding the empty environment. Okay, so that's interesting. So the first lookup here, it seems to be handling the even case, which was going to first hit okay. But it's when it's doing the second recursive call that it's not able to find M in the environment. So that might be in that we're not handling our half closure correctly. Something wrong with the environment there. There still is something I'm not quite getting though, because the apply proc, I'm tracing that, and yet I'm not seeing a call to it. Let me just try thing with that. Okay. Is there an apply proc? I don't see a call to apply proc. Val expr lookup. So this lookup is happening. I thought we were going to have an apply proc before that lookup happened. So there is something confusing to me about what's happening with that version. So let's look at the lookup call. So we're calling lookup. We're looking up even. That's fine. And then the half closure returns false when looking up even. Is that their first? Is that our only called lookup? Look at lookup. Looking up even, and then we look up M. Look up even, and half closure is false when we look up even. Is that within the call to look up even? I'm a little confused here as to what's happening. So I still can't hear you, Dan. All right, so let's see. Find lookup. I'm just going to try to do it the old-fashioned way. Let's just print some things out. So in a call to lookup, calling lookup. This is one way you can debug these things. So we can see, what Y is. And we can see what npat is. Right. And then we're going to p-match on that. And if we're in the letrec case, so there are three cases: empty end, extended end for the letrec end. And in the letrec end case, we're going to see what we have at the half closure. Yeah, and then based on that value, we're going to keep going. All right, so that's probably enough. So I'll get rid of these trace defines and see if we can. Okay. So if I try my test, I call lookup, and I'm looking up the variable even first. Okay, so we're looking up even. That's part of this call here. So we're looking up even because we're applying even question mark to 6. Third try. Okay, so Dan's having some technical problems. I can't hear Dan, although there's some conversation here with Orchid. So Dan and Orchid, or anyone else, have you found what the problem is yet? If so, you can type in chat. If not, right now we're just trying to trace through what's going on. So I changed the example a little bit so that even both we're taking in as the variable, which should be fine, but I changed odd to m, the variable to m instead of n, so we can sort of tell where the problem's happening. So first of all, we have even, I called it even. And so we have to look up the variable even in the environment. So we are looking up even in this environment, which, let's see, here even is bound to a half closure. And the problem here is that we're looking up even using AskQ, and we're getting back hash f. So there's something wrong there. I think that may be the problem we're running into. Let me see if I can figure out what in the world is happening with our AskQ. AskQY, and that list structure. That looks like that should be okay. That's the part I'm not getting. So what? So let me just try reproducing what I think that call is doing. So I think what it's doing is it's calling AskQ on even question mark on that association list. And remember that Scheme won't print out the dots necessarily. Okay, so we should get back that, which is what I expected. And yet, the half closure seems like it's being bound to hash f. I seem to be getting hash f in this case. So why are we getting hash f when we're looking up even question mark? That's very strange to me. That's really strange. Okay, so let's see. Why could that not be working? Try changing let half closure to let HC. You think that's causing a problem? Let's see how that could be a problem. Because those things are just tags. And there's no comma there, but I see why you want to change that just to make sure that that's not going to be a problem. Okay, let's try it again. Oh, same behavior. Same behavior. So let's see. Wow, that's really fascinating. I don't understand why this isn't working. So we're p-matching. Let's look at what we're printing out. This is sort of, debugging is sort of like a detective story, and right now it's not. The story's not adding up. So we're tracing what happens when we look up even. So let me try modifying my test case by the way. So now I'm just calling it with even of 0. So it shouldn't do any recursive calls in theory. And I'm still getting this problem where the half closure is false. So I should be looking up even. That even call is coming from right here. So we're doing a procedure application we're looking up even, that variable, and that should be bound, to this half closure within that letrec. And you can see the letrec environment where even is bound. And yet, when I print out the half closure, I'm getting hash f there. So I'm really confused by that. Why are there commas preceding the vars and the ASCII expressions? Okay, maybe if I get the commas wrong, that would definitely do something. Okay, so the reason there are commas here for F and G and for X and Y and for the bodies is that this pattern is implicitly backquoted. So maybe, yeah, so this is a backquoted expression. And this isn't necessarily the symbol F. This could be even question mark. In fact, it is in our example. And this isn't necessarily the symbol G. This is odd question mark in our example. So that's why we have to put commas there for the pattern matching. We're saying, yeah, we're just giving F. We're giving the name F to whatever we have here, but whatever matches in that position. But that makes me think that maybe there's something going. Well, no, the problem isn't with this P match because we're already in trouble here. It seems like this ASCII isn't working the way we want. That's the part that I don't understand. All right. So basically, there's some assumption that we're making that's not quite right. Let's just try this. Let's try printing out a little more information here. And so I want to make sure, okay, so we've got an env there, that's fine. Let's see, I want to make sure I know what y is still. So y isn't shadowed or anything. Y should not have changed. Let me say, I'm just saying printf in letrec env case. So I know where I am. Okay, so y, I should still see the value of y. I want to make sure that this ASCII is doing what I think it is. So there's something there that doesn't seem right. Let's see. Looking up y in, and now I'm going to put in that backquoted expression just to make sure that everything I think is happening indeed. All right, so let's try loading that one more time. All right, let's try my simple example. All right, so we're calling lookup, y is even. Okay, we're in the letrec env case, that's right. Whoa, y is m. Whoa, 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 what happened there? That's the problem. Oh, I know what I did. I know what I did. I know what I did. Yeah, Dan sees it now. Dan saw it before me. Okay, all right. I know what the problem is. The problem is that. That's the problem. I called it y. We called it y. Okay. So here's the problem. The problem is we're looking up the variable y, right? And what do? We then promptly shadow y to have a different value of y. That was where the m was coming from. Oh, okay. How about I call this fx and I call this gx? Okay, and I'll call this hx. hx. Okay. This is the danger with shadowing here. I think now it's going to work. Maybe. fx is not bound. What did I do with fx? Oh, I had to change them up here. This is fx. This is gx. I should change these the other places as well. Let me And the other half closures. Half closure. X is fine. And then here, yeah, I'm going to call those. I don't want to have the same problem as f of x. And this is g of x. And so this is f of x. And this is x. Okay. Yeah, you have to be really careful of those names. If you shadow accidentally the variable name for what you're looking up, you're going to have a bad time. So let's see if this helps. F of x is still not bound. All right, so where did I do that? fx, fine, and then fx. It's legal to have that dash, right? What do I do now? Did you make another mistake? In the letrec Excel, okay. The code isn't in GitHub, but I should go ahead and post that. Here, I will post we can all play at this game. So git add. This is first order. So this is not quite working version. X bug still. And I'll push that. So if anyone wants to try to play along with this and see what's wrong. Should be close here. I don't know why my f of x. I guess I've got an f of x that's not right somewhere. fx, fx. Why am I getting a unbound f of x? Following lookup. Why is even half closure, blah, blah, blah. In letrec case, why is in? Wait, that's still happening. Did I not reload it? Did not save it? Why is in? Did I still screw it up? I thought I fixed it. Yeah, am I in the right directory? Yeah. Okay, so why is it not working? Okay, in the letrec in case. I'm still doing something wrong. If you see fx but should see even, yeah. Yep. Okay, so there's still something not quite right. It's like the fx is getting mixed up with the f or something. SQ that. H of x. That's the name of the function. All right, what did I do wrong? Oh, it's the letrec end part. You only print fx. Okay, can you give me more context? Above the printf, which printf? All three, okay. Oh, that should be fx. Oh yeah, you're right. I missed one. GX, like that. Yeah, okay. All right. Whew. Oh, that was tricky. Yay, now it passed. Whew. All right, I think I can get rid of these prints now. Chong. Whew. Wow. All right, let me check that in. Oh, All right, well, you get to see kind of how to try to trace these things down a little bit. Yeah, thank you. Yeah, that is a good lesson. Thank you, Orchid. I missed that one. Thanks, Dan. All right. FX related typo. This shows you how you can get into trouble with shadowing if you're not really, really careful with your variable names. Pain-driven development, that's right. Okay, so I think we now finally have a letrec that works. And Dan, you had another test you wanted us to do. So our tests are working now. Was there another letrec test you wanted us to add? Looks like this is all working now. Yeah, all that trouble because we named a variable y. We shadowed the variable coming in. Point out the number of letrec definitions is unbounded. You mean in general? Yeah, in true letrec, in schemes letrec, we can have as many of these functions as we want. We could have 10 or a million mutually recursive functions. And right now we're restricting it to 2. So it looks like this is not too difficult to generalize. Is that right, Dan? We could have as many as we want. Maybe we should generalize it. Actually, it looks quite easy to generalize. Yeah, so maybe we should come up with a generalized version of this, because I think it should be okay. Yeah, because you're gonna always have this structure. I mean, maybe I'll leave it like this with the two argument version, and then ask you to, this is a good thing to try to make sure you understand the interpreter, is to take this version of letrec and extend it to handle any number of recursive bindings. How do you p-match on an arbitrarily long list? P-match works just fine on arbitrarily. In this case, I don't. Oh, okay. I see what the pattern's going to be. I understand the question. So the pattern would be something like we would have bindings or something like that. You would just do that. And this ASCII thing. Actually, I think we just go ahead and do it. I think this should currently work. I think our test should still pass if we do it like this, because the point is when you do the ASCII, that can handle any number of bindings, and you'll look that up. So let's see if this still passes, because I think it will. Yep, that still passes. So so we've started abstracting it. And so, yeah, I may as well check that in. Handling multi-defin letrec. And now we just have to change the interpreter itself, the val expr to also handle any number of arguments. Now the only tricky thing here is we might want to insist syntactically that all of the patterns look correct. So if we're going to do that, what we might want to do is just have a special guard that is going to check to make sure that it's like legal syntactically, like legal bindings. So what we could do is have something like, we can write a little recursive guard called something like legal letrec bindings. And we'll write that in a second. And then basically this whole thing gets replaced with bindings. Actually, now it gets nice and short. I'll cheat right now and say that the bindings are always legal, just to see if we can run it. P-match failed. Okay. What did I do wrong? Letrec bindings. Letrec bindings inv. Okay, so what did I do wrong here? So maybe my guard, let me get rid of that guard for a second, see if that's the problem. Oh, still P-match failed. Okay. Letrec bindings, letrec body. So P-match failed on the even question mark thing. It's the best code for it you've ever seen, Dan? Well, let's see if we can get it working here. I think we're close to having it generalized, but I'm doing something not quite right, looks like. Hopefully it's not quite as stupid as the other problem. Okay, so what was it? Maybe I just need to be a little more methodical. Get diff. I can kind of go back to the old version. I can go back to the old version and just be a little more, a little more cautious. Okay, so let's see. Okay, so let me go back to the version that I think works. And I don't quite have this working yet. Bindings were not dotted pairs. Oh, you're right. Okay, so the problem is here we have a dot, right? And here we don't have a dot, and I wasn't doing that translation. Okay, so let me think about that a second. Okay, so this in Schemely notation does have a dot, but the way it is, it's like a dot and then has another friends around it. That's how this is really equivalent to something with a dot. So basically, if we wrap these things in another pair of parens, then it is in effect the same. The question is whether or not that's classy. You did not create half closures. You did not create half closures. Use map. Do we have to translate it? Oh, yeah, the half closure tag. You're right. You're right. This doesn't work. Okay, so we're going to have a little processing thing. That's fine. That's fine. Okay. All right, that's right. That's right. So let's see. We still want to have our guard. So let's just get all this right. We're still going to check the legal letrec bindings. That's fine. Bindings. Okay. And then this thing here is going to be bindings. But we're going to have to process those bindings. And so now, basically, we have to turn that into this. We have to change that list here into this list here. So we have to have a little recursive function that's going to do that. And so I'll call these process bindings, I guess. And so basically, or I can process bindings or whatever. however I want to do it. I could say like let process bindings the process let bindings bindings. I think that's going to work. Does that sound right, Dan? Using map. You just want me to do it with map. You don't even want it recursive. Fine. Fine. Let process bindings. We'll simplify this code. Let's map something over bindings. And I guess we have a lambda, which takes a binding, and we're going to pmatch on the binding. Okay, and the binding, if we know that we've already verified the binding structure is correct, we'll assume that that's something we've already done. And a binding is going to look something like that. And we're going to return the process binding, which is going to look like the process version. Like that. Does that look right, Dan? I'm free, yes. Okay. Great. Okay, so let me just try running that. Okay, great, that works. Now, the only thing we have to do is, check to make sure the bindings are legal if we want to do that. If we don't do that, then we'll get an error message here in the binding when we process the binding. So it just depends on how good we want the error messages to be, that kind of thing. Yeah, we could use an and map, that's right. So we can say, I think we still have and map, right? And map, even question mark on 468. 478 is false. Okay, and map is just going to map a predicate across a list. So we're going to map a predicate across the list of bindings. Lambda binding, and it's just going to be, so let's pmatch. So if we can pmatch against that structure, then we're going to return true. Else, return false. Okay. Let's see if it works. Seems to work. Okay, so now we should be able to handle letrecs with any number of bindings. All right, so let me check that in. Okay, so this gives you a sense of kind of how like the programming really works. It's all fun and games like when we're doing simple things, but when you get something where like having a wrong variable name is really tricky to track down, then you kind of see how we do it. Okay, and what if bindings is just the symbol quote dog? Then let's add a test. We should, basically what should fail to match with our current version. Rec bad bindings. Basically we'll get a syntax error saying like it doesn't know what the type of expression is. Or yeah, I think that's right. Or it's going to think it's a procedure application or something. We're going to assign goofy. Let's just try that. Let's say letrec dog. How about that? So that should not work. Dog is not a proper list. Oh, the problem's in the and map. That's what you're saying. Yeah, okay, I guess and map. I guess we should be a little more robust because it's not even necessarily a list. Okay, so I guess we can do this. We can do this. This is not the most efficient thing in the world, but we can do this. If it's a list, if the bindings are a list, a proper list, then we can do and map. And if it's not a proper list, then it just fails. Then we shouldn't get that error. Oh, match failed. P match. Did I screw something up? Bindings is a list. And map. Wait, why did? Oh, yeah. That's right. I think yes. So let me go to eval expert. So that we're getting an error from that p match. We'll add another case. Else error. Eval expert unknown expression type, and then we can put in the expression. I think this is where we're getting it. Format. All right. So now we're, kind of in the realm of trying to have decent error messages and all that. So let's see if that helps. Yep. Unknown expression type, letrec, dog, even whatever. Yeah, your class is getting quite an education today. That's right. Okay, so we added some error checking there. I'm not going to keep that around because that's going to error out. But anyway, okay, so let's try it. Let's try a letrec. We should be able to do a letrec that has a couple of different. I don't know. How about a 3 binding letrec? We could do like a little state machine. State 1, state 2, state 3. Okay, so if you're familiar with like regular expressions and finite automata and all that, these are sorts of games you can play with mutually recursive definitions. So actually, let's see. I think there's one with like Pac-Man and ghosts that I think are kind of fun. Well, let's see. Wikipedia state machine. I think there's a neat little example there. All right, here's, but we want more states than that. Is there one more? Yeah. Okay, so here's kind of a neat little trick. We can do sensor opens. That one's too complicated. There's one about like Pac-Man ghosts. Let me see if there's one there. State machine. Oh, here's like a little Pac-Man ghost state machine. Finding state machines. So which page is that in? All right, introduction to game programming. Here we go. So let's say maybe there's like a little Pac-Man. Pac-Man eats power pill. Oh, so these are the states of the ghost. So the ghost is like hungry, and you can eat a power pill. The timer can end, can update movement. This is too complicated. All right, never mind. We'll just do something very simple. So if even, negative, and do flip sign. Oh, so just do even odd and have one more case? We could do that. We could do that. That's fun. Okay, so we could do, I guess, one more case, like another if. Let's see. So we'll have to add like less than or negative or something like that. So the scheme have negative -3. Yep. Okay, so let's add negative. It's like 0, and negative is going to look the same. Negative. Bam, bam. Okay. All right. So if negative of n, then, well, but that's only two states, Dan. It might look on odd numbers. So yeah, but the problem is like there's still only two states that we're toggling between, right? I guess we could call a negative. That's kind of weird. No, what state are you going to call if it's negative? Is it going to call a negative as a function? So we call negative of n. Is that what we're doing? Like that. Well, I'll try writing what I think you want, and then you tell me if it's wrong. So let me do the same thing here for odd. And here we're going to say even. And we're going to have a negative lambda n. No, what didn't do my lambda? Oh, yeah. Should have shown it. Nice. Okay, I guess it's getting confused. Lambda n. Then we're going to say how do we do it then? Well, because we don't know if it's even or odd. Do you pass in the even or odd? Oh, maybe you do that. Well, that'd be one way to do it. Maybe it takes n and a function. This would be kind of fun, I guess. So you could do negative n and even question mark. Ah. Oh, we're not supporting a single argument though, or a variadic though. But we could do curried, I guess. Do this. Being like a little goofy. So we could do f of the negative of n. Does that work? Negative n even question mark. Curry it. That. And negative n of odd question mark. Does that work? That's actually a pretty good test. All right, Dan, is this what you have in mind? The body calls even question mark of minus n. Okay, of like -5, right? Use even, yeah, I am using even, right? Use an even number. No. Won't this work? All right, let me run this in Scheme first of all. Maybe. Maybe is like a good question, a good answer. All right, let's try in Scheme. Yeah, of course that works in Scheme. All right, so the only thing is that curried, the curried thing. Does half closure, presumably the half closure works with curried definitions, right? Oh, we don't have unary minus, so we have to add unary minus, I guess. So we probably have to add unary minus, but that's about it. So let's find unary minus. So it's basically going to be like that, 0. So, or add 1 or anything. So if we have a call to minus that just has one expression, then we just do the Scheme version. So that's fine. Okay. So in Scheme, in case we haven't talked about this or if this was a while ago, the way it works in Scheme is that if you call minus with one argument, it just changes the sign of it, like that. And so I think this should actually work. Unless I left something else out. We got negative defined now. We've got multiple argument letrec. We've got minus, singularity minus defined. Yeah, we'll see if that works. See if it works. That true. Well, it's not true, is it? It's not true. All right, let me just grab that. What is even question mark of 0? That's true. Even of 1. Even of 1 is true? What did I do wrong? I did something really wrong then. If, oh, wait. If negative of n, did I screw something up with my definition of negative? If negative of n, then do this call. Otherwise, if 0, do that. Otherwise, odds of 1. Well, so why is even of 1 giving me true? That's something pretty messed up. Did I screw something up with the definition? Oh, it gives me true in Scheme too. Or what in the world did I do? I screwed something up. If negative, which should be false, right? Then you ask if it's 0. Did I just screw something up down here? That's even. That's fine. You have a bug in odd. Okay. What did I do in odd? Oh, I forgot the base case. So I changed one thing, but I didn't change the base case. Good call. That was a little copy and paste abstraction error. Oh, by the way, types would not have caught that. Or standard types. Okay, so yeah, so let me check the that. Like that, right? Okay, so let's try it now. Hey, it passed. Okay. Negative minus. Okay, -5 and okay, so -5 and let's do a -6. It's not going to be -6, and this should be true in this case, right? Yeah. All right, so we've got a nice classy multi-argument mutual recursive letrec that can, yeah, so we're starting to actually be able to handle kind of a neat subset of Scheme at this point. Yeah, applause. Give ourselves a hand. It was a little awkward, but we got it. And in fact, this is, I think, nicer than the version that we have in the Barlowman interpreter for miniKanren. So maybe it should go back to the relational. Well, when we write our relational interpreter in miniKanren, we'll do this version of it. I think that would be nice. All right, cool. Very good. All right, are there any questions about that? I know that was a little tricky. Let me check this in. All right. Well, thank you, Dan. So Dan, you like this version of it? You like the one we implemented? Applesauce, yeah. But you like this version? Yeah. All right. See ya. Have a good one. Ciao. All right. Wow. Okay. Well, that was quite an adventure. So just to give a recap, what we wanted to do was to add letrec to our interpreter, so we could handle mutually recursive definitions or functions, like even and odd. And so we implemented it using this half closure approach. And we ran into a problem. It didn't work. And so we tried to figure out what was going on. We tried tracing definitions. We still saw, or at least I saw, answers that didn't make sense to me. So just went in and added a bunch of print statements and still didn't make any sense. Like, why are we seeing that we're looking up in when we thought we were looking up even ? And it turned out that we had accidentally shadowed the variable we were looking up in lookup. And so we were looking up the symbol even ? But p match or pattern match pattern had accidentally introduced a variable that shadowed, the y that we were using in lookup, or lookup, yeah. So, yeah, sorry, we're still in scheme. I keep thinking we're miniKanren. Yeah, so we were looking up y, that's y, and the problem was we ended up shadowing that y with, we were calling basically one of these variables y with our original patterns, and that was screwing things up. Or actually, I think it was up here in our bindings. We had something called y. And so that shadowing of the variable we were looking up was problematic and was causing all sorts of weird behavior. So I didn't realize we're shadowing it. And once we fixed that, then it worked. And then we were able to, handle the multiple. Actually, you can see how actually the code is shorter to handle any number of bindings than it is to handle exactly 2 bindings. So this comes up a lot in computer science and math and programming, where the general case is often much simpler than the special case. So we've actually made our code shorter and more elegant, although it's a little harder here to see what the bindings look like. In fact, you can't even see really what the bindings look like. To see what the bindings look like, you have to go down here to the letrec case where we process the bindings, and now you can see what a binding looks like. Looks like that. And you can see what a half closure binding looks like. It looks like that. So we've made it a little more abstract, and we can also handle bindings of any number of arguments. And this allowed us to handle mutually recursive definitions like even and odd, and also, even additionally, to be able to handle letrecs that have 3 definitions that are mutually recursive, or 0, or a zillion, it doesn't matter. Any finite number we should be able to handle now. Okay, so that's actually pretty cute and pretty nice. And so that's this implementation of half closures is quite subtle. Let me just say that this is probably the hardest topic we've come across so far. And don't be surprised if you had trouble following some of what we were doing, partly because we were actually in debug mode and actually had to track down the bug. Although that's, I think, actually a good learning experience to see how we thought it through and what techniques we used to try to debug it. But anyway, this half closure feature is quite tricky. Letrec is tricky in the same way that something like the Y Combinator is tricky. Anytime you have, mutually recursive definitions or recursion or fixed points or any of these sorts of things, tying the knot, it's another term for the sorts of things we're doing. This is where conceptually can become quite tricky. So if you really want to understand what's going on, try to recreate the code yourself once you've actually implemented it and understand it to some extent, and or try tracing through it. Also, try tracing through some examples to try to understand how these half closures work. Those are actually really cute. For a long time, I thought that. What did you think, Dan? That this part was tricky to implement letrec? I thought I had. Had to use a side effect. Yeah, because you can also use letrec. You can implement letrec using setbang, side effect. But this is like a really cool way to implement it, where we're just manipulating the environment in this, sort of the trick. One of the trickinesses here is that we're saving the environment in pat that came in to lookup. That's quite unusual. And that in pat includes that entire, all those bindings of half closure, all the bindings from the letrec itself. So this is kind of the trick, is that the in-pat that we're putting in the closure, in the full closure, includes all of the half closures from that letrec. That's really the insight. And so that's how we get around with the recursion. The mutually recursive definition. So it's a really neat technique. We're using something like that right now in the relational interpreters for Barlaman. But I think the version we implemented here is maybe a little nicer. So, I'd like to go back and revisit that when we get to miniKanren, which actually we're basically at the point where we can get into miniKanren now. So let's see. I guess, I feel like the next, you should destroy the code on the screen. It is totally wrong, right? What code on the screen is right? Wrong. I think the code on the screen is all totally right, and it's all checked in, actually. Everything we have on the screen is running. And it's checked into GitHub. So anyone wants to play around with it, I encourage you to. I'll send you a link, Dan, to that code to take a look at. But I think everything there's fine, and people can try running it. I don't know if anyone's tried running the code, but I'll try it again just to make sure. But it seems to be fine. Good, you sent it to Mitch. All right. Thanks. You sent the good one, I hope. You sent the one I just checked in, I hope. I mean, checked in a couple minutes ago. I'll send you a link while I'm at it, I guess. So we've got this GitHub repo, miniKanren Hangout summaries that has all the code from all these Hangouts. So that's where I'm putting it. We're in Intro Hangout 6. So I will send this link here in the chat. There it is. That's the link, Dan, to those. So both PMatch and the first order interp.scm. Okay, well, I think sort of the natural thing to do now is to move to sort of miniKanren land. We've been talking about scheme. We've been talking about interpreters, how scheme works, things like letrec, scope binding, shadowing. Well, we got a firsthand experience in scope binding and shadowing today with this error and lookup. So we got to live that a little bit. And so now, hopefully you get some sense of what it's like to write a scheme interpreter, how pattern matching works, all those sorts of things. And we could keep doing this. I mean, in Dan's course, we keep doing it for a long time. That's a big part of the semester is playing additional games. We could get into continuation passing. We can get into other sorts of program transformations. We could get into store passing style, so we could handle variables, set banging variables, variable mutation. We could get into the call by name and the call by need. We've seen that a little bit. We could do all of those things. However, what I think would be probably the best thing to do, because ultimately we want to get the miniKanren and see the interpreter in the miniKanren light, the relational light. I think the thing to do is to move to miniKanren, look at the interpreters, build up the interpreters in miniKanren, and then if we want to, we can kind of come back and explore some of these topics that are interesting, but they aren't completely essential for understanding the basic relational interpreter. If you want to generate quines, if you want to run, append inside of a relational scheme interpreter and use it to do program synthesis, for example, you don't actually have to see all of the variants of the scheme interpreter. They're nice to know, and this is nice foundational material, but it's not absolutely necessary to, say, read a paper on miniKanren. So I think probably the thing to do after next week, when I'm not going to be here, but the week after, is to switch gears to miniKanren, get into miniKanren, show what the core miniKanren operators are, get into writing things like appendo, which is like append, except it's a relation, and see what that means and what we can do with it. Get into writing relational interpreters, get into implementing miniKanren and looking at microKanren and building macros on top of microKanren to get miniKanren, all those sorts of things. And then at that point, we can explore any topics we want. We can go back to the interpreter. We can go into program transformations. We can go into, all sorts of things with miniKanren and relational stuff. We can go into Barlman optimizations or whatever we want. Appendo sounds like a spell from Harry Potter. I do believe that someone has created an image of Harry Potter with Dan's face pasted on where he's saying appendo. I believe I have seen that. I don't know if Dan still has that image somewhere. Appendo, that's right. And Evalo, that's the really fun one. So anyway, yeah. Actually, since we ran into that really nasty error with the shadowing, maybe I should not call this interpreter eval. Especially since I'm not calling eval anymore. I'm deleting the eval code right now. That call to eval, or calling the driver function for eval expo eval. That's playing dangerously. All right, still runs. Let me check in the new version. I don't want to spend another 45 minutes tracking down a shadowing error. Okay, so all that code is checked in, and I think this is probably a natural stopping point. First of all, because we threw a lot at you today. This is actually really tricky in terms of the debugging, in terms of probably the hardest concept we've seen, which is how to implement mutually recursive environments over any number of mutually recursive functions using half closures. Right? That's like this is subtle stuff. And I think the next thing to do is to get into miniKanren, but I want to make sure that when we do that, we can kind of pay full attention to miniKanren land. So I think we'll be a little shorter today and just kind of end here. And if anyone wants to hang out and talk a little bit, that's fine. So let's just end it early, because certainly conceptually this was not a light session. And thank you, Dan, for showing up. And I'm very pleased with the version we came up with of the mutual recursion. It was a little tricky getting there, mostly just because of the stupid shadowing error, but that's also a happy learning experience, right? Learning opportunity. So, all right, I will stop the broadcast, and if anyone wants to hang out, I'm happy to do so. See you all, not next week, but the week after. Talk to you later.